Now that we have taken a look at this special case of a mixture of dry air and moisture or water vapor, and we've defined the the parameters that allow us to define how much water vapor we have in the dry air. And by those parameters, I'm referring to the humidity ratio, the relative humidity, as being representative of this two-component mixture of ideal gases. We're now ready to look at what is referred to as the psychrometric chart. And the psychrometric chart is a easy way to obtain the various thermodynamic properties for a mixture associated with dry air and moisture. Okay, this chart is a little bit unique in that it has a couple of y-axes over here on the right, and the y-axis is the independent property of humidity ratio. And recall that humidity ratio is nothing more than the mass of vapor over the mass of dry air. And so it is a non-dimensional number. And so we don't have to worry about whether we're in English or SI. And it is directly related to the partial pressure of the vapor. And that's directly related to the partial pressure of the vapor because a psychrometric chart is drawn for only a single mixture pressure. And in this case, it corresponds to 1 atmosphere. So if you were doing HVAC calculations, let's say in Denver, Colorado, where the barometric pressure is below the 1 atmosphere, you would have to have an appropriate psychrometric chart for that mixture pressure. But because this chart is for a single pressure, mixture pressure, there is that direct relationship between the humidity ratio and the partial pressure of the water vapor that we saw earlier, which had the 0.622 times the pressures. So that's one of the independent properties. The second independent property is the dry bulb temperature, and that is just the mixture temperature associated with the two substances together. And so that is the dry bulb temperature. What else is plotted on this particular line or this particular chart is another scale. And that scale is actually up at an angle here, and it is the scale for the mixture enthalpy. And so that would be enthalpy in units of kilojoules or BTUs per mass of dry air. And so that, if we go back, that was, let's see that was this term right here, the enthalpy of the mixture per mass of dry air. And so that is on this axis right here. Okay. Now, what that means is that if we have a dry bulb temperature and we have a moisture level, a humidity ratio, we have a point somewhere in this chart, and from that point we can then go up, and usually there are lines, scale lines, we can go up and obtain the mixture enthalpy per mass of dry air. What else is on this chart? Well, the various humidity ratios or relative humidity lines are there. Now recall, relative humidity was related to the partial pressure of the vapor divided by the saturation pressure at a given temperature. And so if we have a dry bulb temperature, there is a saturation pressure associated with that. and then the PV divided by that saturation pressure would give us the value of the relative humidity. And so these are lines of constant relative humidity. So the chart is only valid up to the saturation condition, which is a relative humidity of 100%. We have some other lines on the psychometric chart. And one of the lines is the wet bulb temperature. And again, the wet bulb temperature was the temperature that we have if we saturate the air, allowing the air to obtain a lower temperature because of the fact that it's saturated to 100%. And so how do we get that particular value? Well, if we say we were at a point here where we had a relative humidity of 50% at a given dry bulb temperature. Well, again, the process was be that adiabatic saturation process. If I was to add moisture to the air mixture as I cause the relative humidity to go up to a higher value, eventually going to 100%. If I did that in an adiabatic fashion, in essence, what I'm doing is I'm taking energy from the dry air to cause the liquid water to turn into a vapor and join the rest of the other vapor in the mixture until it reached the 100% relative humidity point. And so this line right here is the adiabatic saturation process, and it runs into the saturation, the 100% relative humidity line at a given point. At that point, we then come down and we recognize that that would then be the temperature, the wet bulb temperature. And so we can draw these lines of constant wet bulb temperature. And so if I was at this point right here, my dry bulb would be this, and my wet bulb is actually this value, which would then also be the value directly below. And so that's our wet bulb temperature. So in order to fix a condition on this chart, we just need to have two independent properties. One of those properties could be the dry bulb temperature. It could then be the relative humidity. It could be the value of the wet bulb temperature, or it could be the humidity ratio. Any of those 2 points, and I establish a point on this chart. Upon establishing a point on this chart, just like any thermodynamic surface, we have all of the other thermodynamic properties. One other thermodynamic property that is given, and there's only one line showing that, is this higher slope line that corresponds to lines of constant volume per unit of mass of dry air. So this is the specific volume of the mixture. Again, it's a little bit unique in that it's volume per mass of dry air, not volume per total mass. And so there will be lines of constant volume per mass of dry air on a psychometric chart. And so a full up psychometric chart would obviously have more gridding, and you would have values along this axis here. You would have values along this axis. You would have different lines corresponding to relative humidity. You would have lines of constant wet bulb, and you would also have lines of constant volume or specific volume. And so that is our psychometric chart. What follows here are some bullet points from the textbook talking about the psych chart. And I've already mentioned many of these. One of the things that this first bullet says is that sometimes the humidity ratio, which can be in any unit system because it is a ratio. Sometimes it's actually given in terms of grains of moisture. And what a grain is that there's 7,000 grains in 1 pound. And so you would see the relative humidity, the humidity ratio on that one axis given in terms of grains per pound of dry air. And so it's it's a way of determining the humidity ratio primarily from older times. Again, the mixture pressure is specified for a given psychometric chart. It's necessary to have the correct atmospheric pressure. There were lines of constant relative humidity as shown on the psych chart. 100, 50, and 10 are given there. The air moisture, the moist air mixture is fully saturated at the relative humidity 100% point. Okay, it also talks about the dew point temperature. I didn't mention that here, but if you are at a given point, let's say right here, and you were to change the dry bulb temperature, you were to cool down the fluid without changing the amount of moisture, you would follow a constant omega line from this point. And as you followed that across, as you're cooling down the mixture, you would then run into a point here on the 100% relative humidity line, and that point then would correspond to a temperature that would be the dew point temperature. And we've already defined the dew point temperature. So at a given point, you have a dew point temperature. You also have a wet bulb temperature. And again, the two are different. One is a no change in moisture cooling down until it starts to saturate and condense. And the other one is adiabatically cooling it down and causing the moisture to increase until it reached the saturation point. The one chart here, this line right here, is the mixture enthalpy, and it actually is equal to the air enthalpy plus the omega times the vapor enthalpy. And so those pieces, that chart is actually comes from the various thermodynamic properties associated with the pure substance of dry air and the water vapor itself. There is the wet bulb temperature that I said, and it's shown on the chart, and it can be obtained. And then there's a statement here: the wet bulb temperature is approximately follows the lines of constant mixture enthalpy. And so all they're saying here is that these wet bulb lines here are very close to the same lines, the scale lines associated with the mixture enthalpy. Again, basically stating that this process is an adiabatic saturation process. And again, you'll see that on a true psychometric chart, and I'll attempt to get one of those in the video to to show you. Let's see. So again, these are bullet points from the text describing the psychometric chart. The final item, which I also mentioned, was that there are lines of constant volume per mass of dry air. And so they are lines associated with the specific volume associated with the mixture itself. And we'll see that we can use that to determine how much dry air, what is the amount of dry air in a given mixture, in a given flow system. Okay, so now that we have a way to obtain the properties, it's now time to show the mass and energy balances associated with the fluid. Typically, we deal with flowing systems, even though we can do psychometric problems associated with closed systems. Let's just discuss the flowing system, the control volume type of system. We have a control volume here separated by a boundary. We have an inlet and we have an outlet, state 1, state 2, possibility of liquid or vapor coming in or going out, the possibility of heat transfer into the control volume or out of the control volume. There is a possibility of work if there's a fan. There could be a work component in the energy balance. But for right now, we're not going to assume that there's any work component in the first law. What we know is since we do have two substances and the mass balance has to hold for the two substances, we see that coming in, the amount of dry air, the flow rate of the dry air, is equal to the flow rate of the dry air going out. Again, because there is no additional dry air that is coming into the control volume. That's important. And that's one of the reasons why we develop properties on a per mass of dry air. We then look at the water and we recognize that there is a certain amount of water flowing in here, built into the air, the moist air. There's water flowing out here, again, part of the moist air, but then there's a possibility of a liquid or vapor water being added, and so that's this conservation of mass for the water. Now, if we look at this equation right here, and we just separate and have the m dot water on the left-hand side and take this over to here, we recognize then that each of these vapor flow rates can be related to the mass of the dry air and the corresponding humidity ratio, because the humidity ratio is nothing more than the mass of the vapor over the mass of dry air. So this is a very important equation that shows that if we raise the humidity ratio from omega 1 to omega 2, then that's due to the fact that we're either adding or subtracting water to the control volume. If humidity ratio goes up, higher than omega 1, then it's a positive water addition. If we have the case where the original omega is greater than the final omega, we're actually doing a dehumidification and we're taking water out of the system. So that's our mass balance associated with the air and the water. Now we're ready to do the energy balance. And for the energy balance, we can say that if nothing builds up within the control volume, we have a left-hand side that's equal to 0. We then say that the heat transfer into the control volume is going to be what causes the moist air to go up or down as it then exits, along with what energy came in through the liquid water or the vapor water. So what we have here, this term right here, is the energy associated with the moist air. We see that it's a certain amount of dry air with an enthalpy, a certain amount of vapor with its enthalpy, and so that's what's flowing into the left-hand side. We have a certain amount of water flowing in with a certain water enthalpy, and that's what's coming in at state 3 here. And then what leaves then is the air at a new enthalpy level, because it would be at a different temperature, let's say. We also have the water vapor that is remaining at, again, a different enthalpy associated with it. So this is our conservation of energy, our first law. Now, we obviously can lump some things together, and what has happened is we've taken the m dot A out of this term and this term, and we have then said that the m dot A is times then what's happening to the dry air enthalpy. And then we, instead of having this term here and this term here, we substitute like we did before. We substitute the omega times the m dot air. And so we put in an omega times m dot air here, and that then gives us this term plus then this term right here. Okay. Let's see. No, I misspoke here. That gives us this term right here. And we keep in mind that the HV can be written typically as the Hg at the same temperature. So we made that assumption before, that if we are all out on the right side of the dome at a given temperature, we can usually make the assumption that the enthalpy for the vapor can be related to the enthalpy of the saturated vapor condition at that particular temperature. And so that's how this Hg shows up. It's due to a substitution for here, and this Hg is the substitution for this case. Again, the omega 2 shows up because this is equal to omega 2 plus m dot A. Just like this omega, this particular omega 1 is equal to this term here and m dot A. And then the only other term that we haven't talked about is this term here, and this is the energy coming in, and we know that m dot water from up here is simply related to this term here. Whoops. And so this term gets substituted in, and we see that it corresponds that this m dot water becomes m dot A, which is this term, and then the change in the on the humidity ratio, and then the enthalpy of the water. So what we have in that second equation then is the energy balance, and it's associated with what's happening to the water that's either coming in, that's flowing out, being brought in or taken out, as well as what's happening to the dry air component. Okay, when I come back, we'll take a look at some example problems dealing with air conditioning and discussing those problems and how they relate to processes that can be identified on the psychometric charts.